Okay, so today we're going to be talking about the volume of discs and washers. Basically, we're talking about the concept of rotating one of our flat area shapes around an axis of rotation, which does not have to be the x-axis or the y-axis. It just has to be any horizontal or vertical line that we're going to rotate the shape around so that we get the concept of having a full solid cylinder. If we rotate around a line that doesn't have any space. So if my curve, for example, were something like the cube root of x, then the axis of rotation is x equals 0, will give us a radius from the center of the shape to the outside of the shape. So that the radius is that height between y equals cube root of x and y equals 0. So the idea, however, is that the volume is going to be a cylinder type shape where the cylinder might not always be the same size all the time. So we have to adjust for that. But the volume formula from geometry for a cylinder, volume equals pi r squared h, still applies. We just have the pi on the outside of the integral. The integral of the r squared and the dx are representing really the height. So we're basically going to add up cross-sectional circles, and as we accumulate these circles and add them up as a sum, because remember the integral is basically the idea of doing a sum, okay, it's going to do the sum of all of these circles as the height goes from 0 to 8 in this question. Okay, so again represents pi r squared h. Now sometimes our rotation goes around a vertical line like this one, in which case the height is actually the difference in the y values and not the x values. And so spinning around the circles are going to be stacked up in such a way that instead of having the y value tell me the distance of the radius, okay, so my radius here was determined by the height of the y. My radius this time is going to be determined by the width of the x. And so in this case, we would have to have a function that was a function x in terms of y. So we're still doing the volume of a cylinder as pi r squared h. It's just since the r is changing, we can't just substitute in one constant r. We have to do separate ones and add them all up. And that's how we'll do this, as pi r squared h. Okay, so the rule for knowing whether or not you're doing dx or dy is based on how this spins. So it says the slices are perpendicular to the x-axis. So we're talking about these circles being perpendicular, or the way that this goes. I like instead to kind of think of it, if it spins like this, and this is my height, then it's going to be dx. If the rotation is vertical, like this, then my height is going to go this way, and it'll be dy. So again, it's how the spinning goes. So if the spin is this direction, like the x-axis, it'll be dx. If the spin is vertical, like the y-axis, it'll be dy. Okay, the difference between discs and washers are based entirely off of the fact that this is a washer, like a bolt goes through a washer. It's not a washer like you're cleaning something. It's a washer like putting together parts, and we have bolts, nuts, and washers to do that. So it's more like a donut. So this idea also can flash back to geometry, when your teacher may have given you a cylinder to find the volume, but then they said to find the volume after maybe a hole was drilled out of the cylinder. So if that's the case, and then the height of the interior missing part and the exterior are the same, but what we would have is two different radii. We would have the small radius that determines the inside missing piece, or the hole, and we would have a larger radius that determines the outside edge. So we would have done the volume as volume equals pi, the larger radius squared, times the height, to get the entire orange cylinder, minus the missing cylinder. And the missing cylinder would be a smaller radius times height. So our formula for this, the way that this works, is really we're factoring out the pi because they both have the same pi. And we're factoring out the h because technically they both have the same height. And so we end up with the radius squared minus the small radius squared. And since the radius is the part that's changing in our picture, that's the part that has to be integrated. So this is still pi, large cylinder squared radius, small radius squared, times h. And again, if we're spinning around this way, we'll have a dx. And if we're spinning vertically, we'll have a dy. Now what's important about these, and the reason we put the water glass here, is because we want to know that we're not finding the volume of the empty cup, not how much liquid the cup would hold, but how much material it would take to build the cup. And as thin as this may seem, it does in fact have to have an outside and an inside radius in order to have the wall there. So we're finding the amount of material it would take, not the amount that it would be holding. So again, up here, we would be finding the amount of material in the green part, not the amount of missing material from the center that's a hole. So we're not looking for the hole. We're looking for the entire shape. So really, you can also think of this again as finding the entire cylinder and then subtracting as you drill out the hole or drill out the empty space. Okay, so visualizing here, if I were to have the curve, and in this case we started with the curve that looks like this. This would be the space that's spinning around. And as it spins around, it makes the brown part of the shape as a solid form. So it's a filled in place. So what's missing is the blue part. So the conical shape that's drilled out here is the part that's going to be subtracted. So we're really finding the entire acorn shape filled in solid and then subtracting out the blue missing part. So doing some practice on these, the first thing that says we're going to find the volume of the solid generated by revolving a region enclosed. Okay, so the region enclosed geometrically looks just like when we did area between curves. So the sketch of y equals 2x, y equals 0, and x equals 3 would be this area that we're going to spin. Okay, so now I can notice on here that that would mean the height would be up at y equals 6. But when we spin this shape about the x-axis, that means we're going to do a dx problem. The reflection would show us that there's no extra space from the center to the curve. So if I start at the center of the shape and work my way out, I'm only going to hit one outer edge. So again, this is kind of like having a cone in geometry class. So I don't have an inside radius with this one, I just have an outside radius. And the radius is determined by the difference between the blue curve, y equals 2x, and the blue line, y equals 0. So technically it's 2x minus 0. And then since there's no hole, we just have one cylinder, and it's pi r squared, and then the height is the difference in the x's as we move from x is 0 to x is 2. Sorry, x is 3. Get that down incorrectly. Okay, now if we take the same bounded shape, so we're still starting with this shape, x is 3, y equals 2x, y equals 0. And we spin around a different axis of rotation, for example, y equals 6, we are still spinning horizontally, so this is still going to be a dx problem, but our reflection is going to give us an entirely different shape with a completely different volume. Okay, so now notice on this one, as we spin around, we end up with a cylinder, but really it has a cone subtracted out of the middle. So you're thinking of a cylinder with a cone subtracted. So now our radius has to be determined from the original curve. If you try to use the reflected curve, you would have to write the equation of the reflection. We don't want to write the equation of the reflection, so we always use the original space. So we always start from the center of the shape, and from the center of the shape, if I move out toward the edge, I would have two different lengths. One where I hit the curve 2x, and one where I hit the curve 0. So the inside radius is 6 minus 2x. It's the difference between 6 and 2x. The outside radius is the difference between 6 and 0. So the difference between this determines that length of the radius. So now we have a washer because there's a hole. So we're going to take the entire outside shape and then subtract the volume of the missing part. So that's still pi r squared h. So it's pi, the outside radius squared, minus the inside radius squared. And the height of our shape going in this direction, so we have this direction here is the height, is the difference in the x's as x moves from 0 to 3. Now a similar but very different shape is if we were to draw that same space. So we have y equals 2x, y equals 0, x equals 3, starting at the origin. And we were to reflect across the line y equals 8. Well, now this curved space stops at 6 because we still have to do the region that's enclosed. So we're not going to do more of the space because we're going higher for the rotation. It's the same area, and that same area is spun around this time, y equals 8. So the reflected distance has to remain the same, so I'd have to be 2 units above and reflect this way. So now we have a space that definitely has an entire hole in the middle that's missing, kind of like a funnel. And the radius that we're going to have is definitely 2 radii because we have that space. So we always start at the axis of rotation. Start at the center and determine how far you have to travel to get your radius. So for the inside radius, I'm traveling from 8 down to 2x. So it's the difference between 8 and 2x. The outside radius is the difference between 8 and 0. So we have pi outside radius squared minus the missing part, which is the inside radius squared, dx. And the height, the dx part, is traveling from x is 0 to x is 3. So again, when we're spinning around horizontally, that's always going to be a dx. Okay, so let's look at what happens when we do a dy type question. So we have the same space, the same shaded area that we're going to spin. And this time we're going to spin around the y-axis. So since we're spinning in this direction, we're going to have a dy problem. And again, we looks like we have a cylinder, but a different size cylinder with a cone removed from the middle. Okay, now when we do the radius, we always start at the center of rotation and move outward. So my radius is going to be an inside and an outside, but this time it's the difference between the x's, not the difference between the y's. So we have to convert our equation over. So if y equals 2x, then x has to be 1/2 of y. We also have the equation here for x equal to 3. So going left and right, the inside radius is the difference between 0, x equals 0, y-axis, and x equals half y. So remember when we do these, it's right minus left for the dy questions, versus on top we were doing upper minus lower when we do dx questions. So the difference for this, the length of the radius for the outside part, is x is 3 minus x is 0. So it's the difference between these two lines. The difference for the smaller radius is x is 1/2 y minus x is 0. So our volume works the same way. But this time we're doing a dy question. And so we have the outside radius squared minus the inside radius squared dy, which means that I have to use y values for my limits. So instead of integrating from 0 to 3, we're going to integrate from 0 to 6. Okay, now, if we take the same shape and this time rotate about the line, x equals 3, we have this same shape here where we started at x is 3, y equals 2x, and y equals 0. So it's the same shape. But since we're now going to rotate around, x equals 3, we're still doing a dy question, and the reflection across looks like this. Okay, so since we're doing a dy question, we have to use the y version of the formulas. So x equals half y, and this is x equals 3. Okay, now what that means again though is that we have to use the original equation. If we don't use the original equation, then we're going to end up having to write the equation of the reflection. So our radius this time is just 1 radii, there's no gap. So that means that with 1 radius, we only have the length determined here. But the length is not the length from 0 to the curve, it's the difference between x equals 3 and x equals half y. So we're looking for this difference. So there's no inside radius gap, and our outside radius is right minus left, the difference between x equals 3 curve, or the rotational axis, and x equals 1/2 y. So our volume is pi radius squared. We're doing a dy question. So that means we have to have the y values of the limits. So from 0 to 6. So this time the height is from 0 to 6, so that's dy. Okay, so we're going to take the same shape again. And we're going to take the shape around the line x equals 4. So right now we have this shape from 0 to 3. We're going around the line x equals 4. So that means we have a dy question, because we're spinning vertically. The reflected space has to be the same distance over as we have here. So we definitely have a hole in the middle. So if I'm looking for my inside-outside radius, again, remember I use the original shape. So if I start at the center of my shape and move over, the outside radius is the difference now between x equals 4 and the line x equals half y. So it's 4 minus 1/2 y. The inside radius is the difference between 4 and 3, which notice is always the same. It's always 1. So now my volume is pi. Again, we're doing dy, so it's 0 to 6 for the y values. The outside radius squared minus the inside radius squared. You do have to put your notation, so the dy is incredibly important, because this has to be pi r squared h. The h matters in the formula for volume. Okay, next we're going to do the curve y equals x squared, y equals 0, and x equals 2. Now notice what happens there. If we have x equals 2, which is this vertical line, x squared and y equals 0. Y equals 0 is the x-axis. We do have 2 sides for x squared, but the part that's going to be bounded is only the positive side. So that means that y equals x squared could also be rewritten as the square root of y, but we would have to choose the sides. So I'm going to make sure this is not actually part of what we're doing for this curve. So now what that means then, if I rotate about the x-axis, that we would reflect over, and there's going to be no space, and we're doing a dx. So my radius is from the center of rotation to the outer edge of the original curve. Okay, so that means that I have no hole, so no inside radius, and my outside radius is the curve x squared minus 0. So it's the difference of this height. So this height's determined by x squared minus 0. So my volume is pi. We are doing the x values, so we're going from x is 0 to x is 2. R squared. And what you want to be careful about on here is the r is already squared, so you need to make sure you don't forget that technically you need another square. So it's r all squared. So make sure you actually follow through on that and be careful as you're writing down. Okay, if we take the same shape across the line y equals 4, then this is still our area that's shaded. As we rotate around y equals 4, we will have a dx problem again because of the direction of the rotation. But now my radius is on, my rotational axis is on top, so I have to start at the center of the shape, and starting from the center to the original curve, the inside radius is 4 minus the x squared curve. The outside radius is from the center at 4 all the way down to 0. So we have pi outside radius squared minus inside radius squared dx from x is 0 to x is 2. So the height, again, is my dx. Okay, and again, if we do the same curve with the same shapes, and this time we rotate instead about the line y equals 5, then we're going to have a hole all the way through our shape. So the height of my shape, again, is going this way, so we have a dx problem. The rotation has to reflect across. So now you can see that we have a hole in the center, in addition to a bowled out part. So starting from the center of and going toward the outside of the original shape, the inside radius now is 5 minus the curve x squared. The outside radius goes all the way from 5 down to 0. So it's pi. The height, again, is from x is 0 to x is 2. Outside radius squared minus inside radius squared. Now, it might seem silly at this point to go ahead and write these functions out without simplifying right away. But remember from the area lesson, you want to bank these points. You want to make sure you get full credit for the 2 to 3 points you get for integrals with the correct notation, with the correct limits in the inside parts. So you want to go ahead and bank these 2 points as opposed to risking losing these 2 points and the final point because you messed up the algebra, because not only will your integral be wrong, but your final answer will be wrong. So go ahead and write this down, as silly as it seems, without doing any of the simplification. Bank your points. Okay, so the next problem is going to take the same shape and rotate about the y-axis. That means when we spin around the y-axis that we're going to have a dy problem, because the height of my shape is now going to go from 0 to 4. We also have to rewrite our equation so that it's in terms of y. So if we have y equals x squared, then x is definitely plus or minus the square root of y. But our original curve is on this right-hand side, means x has to be the positive square root of y. We also have the vertical line given to us as x equals 2. So when we're looking for our radius, we always start from the center of rotation and work our way to the outside of the original space. So the outside radius is the difference between x equals 2 and x equals 0. And the inside radius is the difference between x equals the square root of y and x equals 0. So it's pi. Now our height is from 0 to 4, r squared minus r squared dy. Now if we're going to rotate our shape around the vertical line x equals 2, then we're actually not going to have a gap this time. We have x equals 2. We have x equals the square root of y, just this part. And when we reflect our space over, we don't actually have a gap, so we don't have an inside radius. So that means, again, I have to use the original curve. So I have to use this left-hand piece here. Otherwise, I have to write the equation of the other part. So we don't want to have to do that. So we're going to start here and work from the center of our shape to the outside edge. We have one radius, and it's the difference between x is 2 and x is root y. So it's 2 minus root y. So then it's pi. The height is from 0 to 4, r squared dy. So it's pi r squared h. finally on this page, if we take that same shape and this time rotate around the line x equals 4, we have the original line x equals 2, we have the original curve x equals root y, and we have x equals 4. So if we reflect that across, we can tell that we definitely have a hole right in the center, goes straight down. So our radii are going to be from the center to the close edge and the center to the outer edge. So the outside edge is the 4 minus root y. The inside edge is the 4 minus the 2. So this is pi. The height still goes from 0 to 4. So our height here. And then it's the outside radius minus the inside radius squared, each squared, dy. Okay, for our next problem, we're going to sketch 1 plus the square root of x. So I would start with the square root of x and shift up by 1. So the square root of 1 would be 1, and we end up at 2. The square root of 4 would be 2, so we end up at 3. So I would have this square root part. We're also going to use y equals 1 and x equals 4. So this is the shaded region we're talking about. Okay. So we have, again, y equals 1 plus root x equals 4, and y equals 1. So if we rotate around the x-axis, we have to reflect across. So we're going to have the same shape on the other side. We always start from the center of rotation. So this is going to be a dx problem. And go to find our radius starting at the center using the original shape. So the outside radius and the inside radius. The outside radius is the difference between 1 plus root x and 0. The inside radius is the difference between 1 and 0. So we have pi. The height, again, the shape is lying sideways, goes from x is 0 to x is 4. And it's the outside radius squared minus the inside radius squared dx. If we rotate this same shape, which here this is y equals 1, we're starting at x equals 0, we're stopping at x equals 4, and your curve is going to go up to 3. And we rotate about the line y equals 3, then our shape would reflect across, like so. But we always have to use the original shape. So we're spinning around a dx problem, starting at the center and looking for our radius with the original shape. So the inside radius is the difference between 3 and the curve 1 plus root x. So notice I put the parentheses because you have to subtract the entire curve. It's 3 minus all of the curve 1 plus root x. And the outside radius is 3 minus 1, which is 2. So we have pi. Our height of the shape, because it's lying on its side, is still from 0 to 4. The outside radius squared minus, now you can simplify this, but again, you really want to think about banking your points. So minus 3 minus, so I'm not even going to simplify any of it. 3 minus 1 plus root x, all squared, dx. You can always do the simplification later if you have to do the problem by hand. Okay, if we take the same shape around the line y equals 5. So we're starting at 1, going up to 3, stopping at x is 4. And now we're going to rotate about the line y equals 5. Remember, the reflection has to have the same amount of space, so we're going to go 2 steps up to start. And we'd have this shape reflected across. We always start at our center of rotation, our axis, and work our way to the edge of the original shape. So this is y equals 5. So the outside radius is 5 minus 1, or 4. The inside radius is 5 minus the curve 1 plus root x in parentheses. So we're going to have pi. The height of the shape is still x is 0 to x is 4. The outside radius squared minus the inside radius all squared dx. Okay, so we're taking this same shape, and this time we're going to rotate that shape around the y-axis. So going around the y-axis is going to make this a dy problem. So as we convert this over, we want to think about what our equations are this time, but converted. So we have x equals 4 for the original shape, and we had y equals 1 plus root x. So then y minus 1 equals root x, and x is going to be y minus 1 all squared. So now the curved part has to be in terms of y. So starting at the center and working to the original curve, the outside radius is the difference between the y-axis, which is x equals 0, and the straight vertical line x equals 4. So we have 4 minus 0 for the outside radius. The inside radius is the difference between the curve and x equals 0. So it's y minus 1 squared minus 0. Our height this time is going to work from y is 1 up to y is 3. So we have pi, the height from 1 to 3, of the outside radius squared minus the inside radius. And again, this is one of those things where the mistake happens most often, because we're looking to square the entire radius. It's already got a square in it, so a lot of times our brain doesn't want to put another one down there, but it's either squared, so technically it's that radius squared, or you need to remember to make that the fourth power this time. Oops. And so this is dy. Okay, for the next one, we're going to route the line x equals 4. So we're starting with our shape to here, and we're going to go about the line x equals 4. And so when we do our reflection, this time we're not going to have an inside part. What we'll have is the radius starting at the center, going to the outer edge. And now this time, that's the difference between x equals 4 and the curve y minus 1 quantity squared. So we have pi from y is 1 up to y is 3, 1 radius, which is 4 minus quantity y minus 1 squared, all squared. So it's the entire r squared dy. If we were to take this same curve about the line x equals 6, again we're starting at y equals 1. This is x equals 4 up to y equals 3. Rotating about the line x equals 6. That's our axis of rotation, the middle of our shape, 2 units further over. So we're going to get a very different volume. Okay, and the reason that we're getting a different volume is because this is going to spin around like fan blades and take up a much larger space. So this is like a small bagel with no hole, or it could be like a small pastry, whereas this is a giant donut. So the volume's going to be bigger for the donut, even though it has a hole. Okay, so now we always use the original curve. So that means we have x equals 6 for the center, but the original curve is x equals 4 and x equal to y minus 1 squared. So the outside radius is from the axis, the difference between the axis of rotation, which is 6, and the curve y minus 1 squared. The inside radius is the difference between x equals 6 vertical line and x equals 4 vertical line. So we get 2. So it's pi. The y values travel from 1 to 3 to make the height of our shape. And it's the outside radius which is 6 minus, parentheses, y minus 1, quantity squared, all squared. So that's the r squared minus r squared dy. So you don't want to spend time foiling this out. You don't want to spend time trying to turn this into something else in case you make an algebra mistake and then lose all your points.